Hey, good morning, good afternoon, or good evening. Welcome to another edition of NoCode Data and AI. We are broadcasting live from Washington, D.C. today, but this will be recorded and available later on YouTube and maybe on iTunes. I'm going to try to go through the topic in a way that you can listen to this and get something out of it. If you have any questions, just feel free to ask them in the YouTube chat, and Akwi will try to relay those back to me. If I don't get to them during the session, I will be sure to answer them afterwards. So I have my presentation up and running. Yeah, today we're going to be talking about retrieval augmentation, or also known as data augmentation in the world of large language models and AI. And though we're going to be really thinking about the design pattern and the way of thinking involved in how this all works, we'll touch on a few frameworks, which will be covered in more depth later in subsequent sessions. And I think we're ready to start. Qui, just let me know if it's coming out okay.
Coming up.
All right. Yeah, so the design patterns we talked about last week were based on user interface design patterns. Today we're going to be talking about design patterns in retrieval augmentation. And retrieval augmentation is really what is making large language models very accessible as a way to make intelligent applications or intelligent platforms. And that's why it excites me, is that it's much easier to grasp and use than using traditional machine learning methods. So what is retrieval augmentation or data augmentation? It's basically using your data to get an LLM like OpenAI or Cohere or Anthropic or Bard to give you a more accurate answer because it's your data, it's your facts, right? If you didn't give your data, it really isn't aware of your data, of your information, so it could just make up an answer, right? It's called hallucination. And it's not just your data. Technically, you can augment an LLM with the current stock information, the current weather data that's out there, whatever information that the large language model has not been either previously trained on or has not been fine-tuned on, you can augment it at runtime. A little shameless plug about our company, Anant. We work with platform owners and leaders that need help scaling their platform to global scale. We have launched Kono.io as a center of excellence around large language models. And we have an ongoing call to action for you to fill out our survey for the bootcamp, where we plan to hold it is based on where people want it. So we definitely are starting a virtual bootcamp in the next couple of weeks, and be on the lookout. It'll be also on that same webpage you see, kono.io/bootcamp. And we'll also be putting the information up on the meetup, as well as all the Eventbrite sites that we have. And the agenda for the bootcamp is two parts, or really it's four parts, but it's two major segments. One is about theory and strategy and design patterns. And in fact, we're talking about one of the sections of the bootcamp today. And then the other part is based on more on code and hands-on examples that you can use what you're learning. Today's agenda, we're going to talk about retrieval augmentation. We're going to then look at a basic example of retrieval augmentation with like a regular database or or if you can imagine like a search index, a traditional search index. Then we're going to talk a little bit about vector databases and embeddings, and why they're useful in the machine learning world in general. And then we'll talk about the design pattern of how to use a vector database. And between basic database information retrieval and augmentation and a vector database retrieval augmentation, you can pretty much do anything. You don't even need a framework, like we'll talk about LLMindex and LangChain in brief today. You can actually do all of that with regular code. Whatever programming language you happen to like, you can use. You don't have to use any of the open frameworks. Retrieval augmentation is, as I mentioned earlier, a way to get an LLM accurate information in the context of the prompt so that it gives you an accurate answer back. The trick is basically, how do you give enough information to the LLM that it can give you the right answer, or the answer that you want, but at the same time be in the context length limit of the LLM. If your database has billions of records in it, and you want an answer on billions of records, the context length is not going to fit all that data in there. Now, if you ask a question which may be related to some of the information in your database, then technically you could take your question, figure out what part of your database to pull, the relevant information, and give that to the LLM. Hopefully it's in the context length, and then the LLM is going to give you an answer back. You may ask, well, what if I want an answer about all the data? Well, the LLM is not really meant for that. There's regular data analytics with SQL and Spark and data frames inside Python that are perfectly well suited for answering questions about structured data. What the LLM is really good at is answering questions about anything, structured, unstructured data, but they have a limit. They're really smart, but they have a limit, right? So just as you wouldn't give a person 30 books and say, I want a summary right now, you wouldn't give an LLM billions of records to analyze. The context length limits, at least right now, won't fit that information. And it just would be bad design. There would be different ways to actually manage that task with LLMs. And we'll cover a little bit of that today, but really that's a different challenge. Vector databases are a way for us to streamline that operation of getting the relevant data. And whether you're using databases, search indexes, like relational databases like SQL, or non-relational databases like Cassandra, or search indexes like Elasticsearch, the same general patterns apply. It's just that when we use vector databases, we have one more step to consider, which is embedding our data into vectors when we load the data, and then embedding our queries when we are trying to find similar documents. And we'll cover all that. At the core, retrieval augmentation is about information retrieval. For the data that is not in the trained LLM, we can get it from another source. And that could be from an API, a database, a search index, files. It doesn't really matter. Information retrieval is just retrieving information. And there's a whole branch of computer science focused on information retrieval. Really great books out there. At the end of the day, we are trying to make a context in our prompt. And we had a session before about fundamentals of LLMs and what a prompt is and how you can use a general formula to get good answers. So you can watch that on YouTube. But we're using information retrieval to have contextually relevant data. And contextually relevant means when you're asking a question, relevant to the question that you're asking, or an instruction that you're asking, right? For example, if you wanted to get a summary of, certain customer reviews for a restaurant from Yelp, what use is it to send every single customer review on Yelp if you really care about just that one restaurant, right? And information retrieval can be done in many different ways. So as long as we're giving contextual relevant data, whatever method you use is good enough. It also gives us enhanced capability because it's not just one type of database. It could be external systems, external APIs that you can get data from your system, you can get data from external systems and bring that together. So, for example, if you have a document or documents inside your Google Drive, and you also have data inside your CRM, like HubSpot or Salesforce, and you want to synthesize some information between these two sources, information retrieval will allow you to get the data, as long as you're getting relevant information. Let's say for a customer, you could find the customer in the CRM via a particular search. You could find files inside Google Drive via search. You bring the data together, you send it to the LLM, and you get an answer back. Whereas you wouldn't be able to do, that without adding your own data. But again, the same concept, information retrieval is not just about stored data on our disk. It's beyond that. It's any data that the system can talk to. And what that really gives us is the magic of dynamic learning. Traditionally, in traditional machine learning, when we had to train it or use new data, basically we had to retrain our model. Now, as long as the data comes into the database that we're working with, or the vector database that we're working with, as long as it gets there right before we ask the question, we're able to then leverage that information. That's really powerful. And by the way, this is not just for data. When you combine the ability to store different types of prompts in a database, then truly the LM is getting better and better because the prompt is the magic that makes it all work. I'll review the React method here because it's the basis of something like LangChain. It's essentially the basis of a lot of these LLM frameworks. And the React paper, this has nothing to do with the React user interface framework from Facebook. The React paper, which is React being short for reasoning and acting, it builds on something called chain of thought reasoning. And it takes a person's request, breaks it down into a chain of thoughts. And then depending on what is the best course of action for each thought, it can either try to answer that question inside the LLM itself, or it can go to an outside source to get that information. The example from the paper is asking a question, aside from the Apple remote, what other device can control the program Apple remote was originally designed to interact with? And if you ask an LLM this question, your answer that you get back is iPod, and it's wrong. If you do reasoning, you say to it, let's think this step by step, and that's a magic term, by the way. You just add it to your prompt and it will give you a better answer. And more than likely, if it doesn't have access to relevant information, it's again going to give you an answer that's kind of makes sense, but it's not really correct. And the other, pure action-based method is you don't really use the large language model at all. You just search your data. And in this case, it searches for Apple remote, it gets something, it searches for, something else called front row, which is related to it. And it says, hey, this is the answer, right? And that's not going to work either. And again, this is a simple example, but you can imagine like Google, right? Before ChatGPT, you would have to go find several things on Google and then because you're a reasoning person, you can determine if a thing is relevant to what you're asking, and then you can use what it's giving you. So what React is basically doing is saying, let's take this idea of chain of thought, reasoning, break down the task into the simpler components, and then based on the task, ask ourselves, or the LLM is asking itself, am I best suited for this? And if it's not, it says, let's look somewhere else. And it can combine action, going to a different system, getting data, and understanding the output of that, and then continuing down, looking at other results and saying, do I have the answer or not? Until finally it does come up with an answer. And this is, kind of a more advanced retrieval augmentation, obviously, because we're inserting the ability to reason with the answers. Today, we're going to talk basically about, basic retrieval augmentation with a database, or basic retrieval augmentation with a vector database. But it's important for you to understand that retrieval augmentation eventually needs to be in this context of something like React or chain of thought. Otherwise, you're getting something that can go Google something, or can find a database answer and summarize it, or do something specific with it, and it's really that's it, right? It's not going to give you much more intelligence than that. So though we need to understand retrieval augmentation, we really should be thinking about something like React, which is a way to ask a question and have it answered through a step-by-step process. In general terms, retrieval augmentation with an LLM involves your code interprets the user's query. And in the diagram, I'm going to show you the code is just framework. Then your code talks to the information retrieval system. And it can search it using, let's say, Elasticsearch or TypeSense or Solr. It can do a SQL query, or even an API call. Now, if you're not using something like LangChain, the onus is on you to understand how to take the user's query and translate it into an SQL query or an API query. Technically, a search index, you could just take the user's query and then just send it, right? And you can also do this, and there are tools and chains that do this, and we'll talk about it when we talk about LangChain. You could take the user's query, translate it into an SQL query, because the LLM is capable of writing code, use that to then ask the question from the SQL database and bring it back. But that's outside the scope of just explaining information retrieval, right? So your code intercepts the user's query, tries to find relevant information. It then uses that data that it gets back and constructs a prompt which has your query, your question, or your instruction, the context that it retrieved from your database, right? So that's the constructed prompt. It sends that to the LLM, and it gets the answer back. It can format it if it needs to be, and it sends it back to the user. That's basic information retrieval with LLM. Looks like something like this. You have a user, asks a question, the framework constructs a prompt. I will say that's the augmented prompt. It then sends that prompt to the LLM, right? Gets the answer. Now, somewhere in between, it's getting data from a database. It's requesting data, relevant data, it's retrieving that data, and then it's constructing the prompt. Pretty straightforward. If you can imagine, the only thing that you really need to know here is software engineering. And if you're a software engineer, you know how to use databases. If you're not a software engineer. I'm sorry. It seems simple enough. Now, vectorized data augmentation, it's slightly different. It's not that much different, but it's slightly different. We have to pre-process our data into a vector database. And we'll talk about why in a second. but just stay with me here. And we need an LLM's help to do that embedding, because the LLM has an algorithm that's created out of the neural network that can take words and map them to numbers in a n-dimensional vector space. You can't really visualize an n-dimensional vector space, but just imagine three-dimensional vector space, and each word, each sentence, each document basically lives in some space because it can be vectorized into numbers. Your code then, when a user is asking a question, embeds the question with an LLM, the same way that you had pre-processed your data into a vector database by embedding it and storing it in there. And it takes the embedding of the question and it finds similar documents from the vector database. Now, vector databases have similarity search built in. So if you have, well, most of the good ones at least, if you have vectorized data inside a vector database and you have your query and you vectorized it, you can find similar documents. Another approach that people take is they take the query that the user asked, they tell the LLM to create a hypothetical document or answer first, they vectorize that, and then they find similar documents. Sometimes that actually works better, but that's called hypothetical document embedding. HYDE is a short name for that. When it finds similar documents, it then adds the relevant context, sends that constructed prompt to the LLM, gets the answer back, formats it, sends it back to the user. So very similar to basic information retrieval. It's just that we have to pre-process the data first. And actually, vectorized data augmentation, actually very similar to building search indexes. If you want to do a really good full text search and your regular old database can't do it, you have to take that data and you have to put it into something like Elasticsearch or Solr or whatever Lucene-based index out there, or if you have a proprietary search index, right? So if you've done search indexes before, vectorized databases are very, very similar in process, but there's an element of using an LLM that facilitates that process. So what are vector databases? Why do we have to vectorize our questions, or why do we have to vectorize our documents? Well, vector databases seem like the best memory for machine learning. You can take any data, not even just words and sentences, and using an encoder, like a deep learning model, like let's say Ada from OpenAI, or BERT is another one that's open source, and come up with vectors, n-dimensional vectors that represent that document. Okay, and why is that important? Well, inside the LLM or any machine learning model, your images, your words, your sentences, they don't end up as those things. They are actually all vectorized into numbers. And those numbers are what the whole thing is trained on. So when we can vectorize something and store it in a vector database, it's actually closest to the internal workings of a machine learning model. Now, the really fascinating thing about this is that you can use basic Euclidean math, even though it's beyond 3 dimensions, to find the distance between documents and then rank it. And there's different algorithms. You can do cosine similarity and dot products and things like that. But the point is that these are all built into vector databases, and you say, you pre-process your data into the vector database. All the numbers are in there that represent documents. Some vector databases also allow you to store the text with the vectors, which is technically your metadata. But you don't have to. You can store the numbers inside the vector database and a reference to your actual document elsewhere. And when you ask a question to a vector database saying, hey, can you find similar documents related to this query? Or you expand a query into a hypothetical document with the help of an LLM, and then you say, find similar documents. It finds documents that are relatively similar. And you know what? That actually works for pictures as well. It's not just for words. In this case, we're using large language models. We're really just talking about words and sentences and paragraphs. But the same underlying knowledge can help you, for example, find similar pictures. It's kind of cool. The first part of vector information retrieval augmentation is we have to take our data, and whatever our code is, we'll say our framework, it takes the document, sends it to the LLM, gets embeddings, and then stores the embeddings into the vector database. If the vector database allows us to store the document itself, we'll put it in there so that when we retrieve the document, when we search for the document, we don't have to then go to another database and find the actual text. Looks super simple, but there's some tricks here that we need to be cognizant of. Remember the context length, right? This is the whole reason why we're using a vector database or information retrieval to find relevant documents and not sending everything we have. If your document is a whole book, yes, you can embed it. Well, may not be able to embed it if the LLM can't support a big document, right? But let's just say that you find a way to embed your whole book and you put it into vector database. Technically, that's not really great for you because anything that you're looking for could be matched in that whole book, right? So there's a whole science of, and a little bit of an art of, how do I break up my documents into smaller and smaller chunks and store vectorized representations of the chunks, and then a reminder of where that data is. And there's different ways to manage this. Some people take a big document like a book, and they will get summaries of each of the chapters, and then store that. They'll vectorize that, and then they'll also chunk up all the paragraphs and they'll store that. Sometimes they'll have overlapping chunks so that whatever the thought is not broken, right? So you can have overlapping chunks that you can give to a LLM, and they'll figure out that there's an overlap, right? It won't really complain too much. Once your data is in a vector database, very similar to information retrieval based from a database or an index, we still have the same general flow. User asks a question, goes to the framework. The framework, instead of just going and getting documents from the vector database, it first goes to an LLM to get an embedding, gets the embedding, find for the query or for a hypothetical document, if that's what you do. And then you find similar documents from the vector database. You construct your prompt, and that's your augmented prompt. You send it over to the LLM, and you get a response back, and then you send it back to the user. And that's it. You guys can now make really amazing applications. Well, there's a lot more, but essentially that's it. And this is why, again, I keep coming back to why are LLMs so powerful? They're not only just great for end users to use in ChatGPT, it gives us now software developers that don't have a, necessarily, I do understand machine learning, but let's just say you didn't understand machine learning. You don't need to understand machine learning to do this, getting data into a database and getting data out of a database, right? That's all of IT basically. Yes, there's some nuances of embeddings that you may have to learn, but you can do this. You too can do this. Real world example, and in this case, we're looking at Llama index, right? So the top part of this is the loading part. So imagine we have data from Slack, we have stuff in Google Docs, we have maybe some exports of data from a CRM. Well, Llama index has loaders for Slack formatted data. It has a Google Drive loader. It has a JSON loader. And it takes that and it breaks it apart into, documents, and it can have a document index. And then once it has broken up your source data into something that it can manage by itself. It then goes and chunks it. It can even summarize it for you if that's an option you choose. It can then embed it and then load it into a vector database. And this all is part of Llama Index. Llama Index is, I don't want to say just because I think it's very powerful, but it's just a framework to help you load data into a vector database without knowing all the ins and outs of what I was talking about earlier. And once it's in that vector database, Llama Index can also help you take the query, embed it, find similar documents from a vector database, or if you're using the summary option, it can look at the summaries first, and it can get relevant data and send it to an LLM. You get the response, and then you send it back to the user. And again, all that is inside Llama Index. So if you can use a Python library, you too can do this. All you need to have is a vector database ready to go, an LM key, and you can go to town. When we do our bootcamp, we will be using these libraries and these frameworks. And it doesn't really matter what programming framework you use. Technically, you can use any programming language. If you use Python, you have access to something like Llama Index. If you're using other languages, there's probably some people out there that have made similar tools, or at least some code that you can get. Before LLM engineering, machine learning was very hard. Here's an example of a real-time machine learning platform where you have data coming in from outside systems. You have some sort of batch ETL, ELT process. You put it into a data lake, and you have to featureize it and store that in a feature store. If there's streaming data coming in, you have to get data, you have to featureize it. And then you can train your model based on correct, pairs of whatever your data is and what the outcome is that you're looking for. And that requires real world machine learning engineering, MLOps knowledge. And that can be done in real time or in batch. And then after you have a model that's trained, and can't be trained all the time, but you train it every so often, you then have to store the model somewhere. That's your model registry. And then your application developers can talk to the model, get a prediction or an evaluation in real time or in batch, and store it somewhere, and then look at it. So to do machine learning traditionally, you have to have people that knew data engineering, data ops, machine learning ops, machine learning engineering, and then of course application and software engineering. Now, making intelligent platforms a lot easier. Though this is a slightly more complex document, vectorized pattern that I was showing earlier, it's basically the same thing. In this case, we have outside systems, we have an ETL, ELT pipeline. We put that into a scalable data store, we vectorize it either in real time or in batch into a scalable vector database, using a pre-trained model for the embedding, and then after it's stored in the vector database, our application developers can use the pre-trained model to again embed the query, find similar documents, send that document to the LLM, get an answer back, and give it back to the user. And you can read more about how to build an infinite scale AI on Planet Cassandra. I posted an article last Friday, and as I continue doing this bootcamp series, I'm going to post articles that basically mirror the concepts we're talking about, but at infinite scale. We're not going to get deep into the frameworks today. My goal was just to get you to think about retrieval augmentation and convince you that it's cool and important. And if you're on the edge of the cliff of jumping into LLMs, hopefully this convinced you that you don't have to know a lot of machine learning. You just need to know how to program. Llama Index, which I gave an example for earlier, it's great for loading documents in a vector database in different ways and then asking questions against it. There's a lot of open source projects that have just used Llama Index to, quote, talk to your documents. LangChain can use Llama Index to talk to your documents, but LangChain can also talk to outside systems like APIs and other databases. It can take your query and make it into SQL and talk to a database for you. But that's beyond retrieval augmentation. That is doing other cool stuff, chain of thought. And then semantic kernel is, I think, the most mature from Microsoft. There's a Python version and so Llama Index and LangChain are both in Python. LangChain has a TypeScript JavaScript version. Semantic kernel is available in Python and in C#. C# is a ton faster than Python, by the way, guys, if you don't know that. But semantic kernel has a different approach to how to work with LLMs. I really like how they've broken it into skills and functions, and you can define these skills, and skills are basically, prompts. But the cool thing in semantic kernel is that you can use other prompts inside your prompt, or you can use functions inside your prompt, and you can define these in code or in prompts, and it's super cool. So when I go through semantic kernel, you'll see me geek out about that. Key takeaways: core of LLM frameworks these days is retrieval augmentation. If somebody says they have an LLM framework and they're not talking about retrieval augmentation, they're probably talking about how to train the LLM. Right? That's LLM ops. When I think about LLM framework, I'm thinking about retrieval augmentation. That's the core of it. So the first pillar of retrieval augmentation is made up of prompt engineering. You need to know how to do prompt engineering. If you don't know that, you can watch a previous video that we have. Go to YouTube. There's tons of great people talking about it with a lot of hype. I'm not a hype person. Second pillar of retrieval augmentation is made up of data engineering, basically how to prepare the data. Data engineering, there's a lot of people that have data engineering backgrounds. Welcome to the cool table. Now you can do machine learning also with just your data engineering knowledge. I would say that data engineering is what makes big platforms work. End of story. So if you didn't have really great data engineers, you would have crappy platforms. The last pillar of retrieval augmentation is basic software engineering. Once you prepare the data, how do you sequence user interactions with the LLM, with the databases, with the vector databases? I encourage you all to try it out on your own first. So in the OpenAI cookbook, there's tons of examples that use vector databases and basically shows you how to do this by hand using whatever programming language you like. But if you want to do anything of consequence and you want to build something useful for people to use today, the open frameworks are a great starting point. You can take other people's code that are using these frameworks to get started. In one of our future sessions, we'll talk about open source apps that run on these frameworks that all you have to do is run in a Docker container, and you will have a talk to your document. There's a thing called DocsGPT. And you don't have to pay somebody to use their software. You have to pay OpenAI, but that's about it. Thank you, and dream big. If you're interested in some of this cool stuff we're talking about, you're more than welcome to hire us. Go to anant.us for our playbook. I should also add on here, Kono.io. We have a curated feed of videos, not videos, excuse me, links that I'm saving every day, every hour that are useful, related to LLMs and general software. There's also a stream of videos. So if you want to see what videos we've done, you can go to Kono.io and check it out. And if you're interested in getting invited to the Discord channel, please drop your email or drop your Discord user ID, and we'll invite you and you can talk to us about LLMs. And that's it for today, Akwi.